Hello and welcome to Mechanics of Solids 3321. This is your Section 1 instructor again. So I'm going to be doing a couple of problems using the graphical method. Example number 6 and example number 7, which you see here on your screen. It's number 6 and this will be number 7. And we're going to be using again the graphical method. So before we begin, we have to understand the following. This particular set of method has to implement a certain criteria, and the criteria is given to you on your PowerPoint presentations. And it's basically stating this right here, ladies and gentlemen. It says right there that in order for you to get your shear equation, you have to integrate the distributed load, but the negative distributed load. And that is basically what causes slopes. So a constant distributed load will cause a negative slope. So what exactly does that mean? Well, let's take a look at the first problem, which is example number 6. So this guy right here, let me go ahead and draw it real quick on a sheet of paper, and we'll go ahead and get started. So I went ahead and did this quick drawing. Let me go ahead and switch screens. This is example number 6. Example 6. And basically what we want first is for us to determine those reaction forces. Reaction at A, reaction at B. That's pretty much it. So before I begin, I'm going to substitute this distributed load with one resultant force. So that's 100 times 2. That is 200 newtons. There you go. So I'm not going to be using the distributed load. But again, this is just for the purpose of me finding out what those resultant forces are. This distributed load is very important for us, for me to have an accurate shear and moment diagram. So let's go ahead and solve for reactions at A. So reactions at A, and I'll use sum of the moments about point B. It must be equal to 0, positive, and then basically usually start from left to right. This is positive 50 Newton meters, and then I have RA producing clockwise, so that's negative RA, a distance of 4 meters. Then I have this 100 Newton force also producing clockwise, which is negative 100 newtons, and it is at a distance from B of 2 meters. I'm going to continue here in the bottom, right here. And then I have this 200 newtons producing counterclockwise, so that one's positive, 200 newtons. And that one's at a distance of 1 meter from A. And then that's pretty much it, equal to 0. Which gives me a value of RA being equal to, let's see here, of about 12.5. There you go, 12.5 newtons. And then by doing a little sum of the forces in the Y must be equal to 0, I can easily find out what my RB is. So this is 12.5 plus 100, since it's going up. These are all newtons, minus 200 plus RB equal to 0. And this gives me a value of RB equal to 87.5 newtons. So these are my reactions. All right. So this is how simple it is, guys. I think the part that takes you the longest is for you to find out what your reactions are, believe it or not. First things first. External loads or reactions, such as this one, and this one, produce jumps in your shear diagram. So again, I repeat, external loads and reactions, such as this one, and this one, produce jumps. Distributed loads that are constant produce slopes. So this one, for example, is a constant 100. That is going to produce a slope of negative 100 x. So if you recall from the slide that I show you, it shows you that when you take the integral of negative the distributed load, you're going to basically get 100. And then when you take the antiderivative or the integral of that, it's 100x, but it's the negative. That's why distributed loads that are pointing down are going to give us a downward slope. Now, a triangular distributed load, which already has a slope, will give us a quadratic equation. So let's go ahead and get started. So again, these produce jumps. Our very first jump is going to be 12.5. So we actually start at 12.5. And then basically that's constant, 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 and then boom, another jump of 100. So this basically is constant, 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 and then boom, a jump of 100. So we're going to be over here at 112.5. 112.5, way up here. And this is where our distributed load starts to happen. Remember that for our shear diagram, we do not use our resultant force from our distributed load. So what is this slope? Again, it's a negative 100x. So it's going to be basically doing something like this, just down. But how far do we go? That is a question. Well, if you think about it, if we start right here, how far does this go is basically answered by the following equation. If this is a slope of negative 100x and you go a distance of 2 meters, how far have you traveled down? So it's basically 100 times 2, which is 200. So for every 1 meter, it drops down, you know, rise over run, rise over run, rise over run. So for every 1 meter, it drops down 100. So the fact that you go 2 meters, it drops down 200. So if we are at 112.5, it's going to go all the way down here to all the way down here. So we subtract 112.5 minus 200, and that gives us a negative 87.5. There you go. Which makes perfect sense because our last jump, oops, I'm sorry. What the heck is this? Postpone. I don't know how long that was there. Sorry, guys. Okay, so again, this is a negative 100 slope for a period of, or I'm sorry, for a distance of 2 meters. That brings us down 200. So if this is 112.5 minus 200, that's negative 87.5. And it makes perfect sense because look at our last jump. Our RB pushing up is 87.5. So it takes us back to 0. So this is basically what our slope looks like. Obviously, you do not need these arrows. I'm just going to put them in here, kind of just to signify our little jumps right here, our external loads, our 12.5, our 100, and our positive 87.5. So I start at 0 and I end at 0. Again, these are not required, and they usually you don't show those in shear diagrams. You just show this one, and that's it. Now the next thing I'm going to do, I'm going to find out the areas under those curves. Because remember, when we go from our drawing, we take the integral of this, and it becomes that. And then the integral of this basically becomes areas under the curve, if you know your calculus. So let's go ahead and find out what this area is. This is 12.5 times 2. That will be 25. I'm going to call this area 1. It's 25. This is a triangle right here. And the question lies in where exactly, how wide is this base? Where did it touch, question mark, the x-axis? So I know this is 2 as far as distance goes, and I know this is 4 meters. This is my x meters. But where exactly did it touch? So you have two choices. You can use your ninth grade or 8th grade Algebra 1, if you have 2 points and you know the slope, you can come up with an equation that is basically the point slope formula. I'm sorry, I'm kind of stuttering over here. Y minus y1 equals to mx minus x1, and you can basically solve for the equation in y-intercept, and then find out when y is equal to 0, and that will give you your location of your x. So that's one way to find out. Okay? All right, so I took a little time right here. I went ahead and made this point 2. That's my x, and 112.5, and I made this other point 4 and negative 87.5. So by using the point slope formula, I was able to come up with the equation of this line, which is simple negative 100x, which we already knew was a negative slope of 100, plus 312.5. And if we set this equal to 0, we can actually find out exactly our x location that this intersects. And that is basically 100x plus 312.5. That's when x is equal to 3.125, or 3 1/8. So the distance between here and here is 1.125. In other words, this x is equal to 3.125. So now I can find out my area 2 of this triangle, and that is base times height divided by 2. And that is about 63.28 125, well, whatever. That's good enough. That will be Newton meters. Of course, when you're multiplying newtons as your height and meters as your base, you end up with Newton meters. And then this bottom piece over here, if this is 1.125, this is basically 0.875. And then, of course, this height is 87.5, so you can actually find out this third area of this bottom triangle. And keep in mind, this is negative area. That is very important for you to understand that. And that would be negative 38.28125. But this is good enough. So again, positive area, negative area. Why do I need that negative area? Well, because that's definitely going to help us with our moment diagram. Our moment diagram is very important. You can actually see the other problem that I was working on. Let's see here. There you go. So, for our moment diagram, we have to come in with the understanding that just like these guys produce jumps, they produce jumps in our shear diagram, these guys also produce jumps in our moment diagram. This is the only part that is counterintuitive. We usually consider counterclockwise to be positive. This is the only time. Again, I repeat, whenever we see a counterclockwise moment, it's actually a negative jump. So we actually, since we're starting from left to right, this is a negative jump, and it just starts at 0 and it jumps down to negative 50. This is again for your moment, and your units are Newton meters. This is 2 meters, this is 4 meters, this is our x in meters. What do we do after that? Well, we have a constant shear. And remember, when we take the integral of that, constants become slopes. So how much is this slope? It's actually, 12.5. So you can either do that, or you can just add this area. The area is 25. So from negative 50 plus 25, you go to negative 25. Negative 25. And basically you just make your straight line right there. There you go. And this is where you're currently at. So Nothing here. So this is constant. Constant produces a slope. Just like this one's constant, it produces a slope, and therefore this slope is going to produce a parabola. So this slope right here is negative 100. Negative 100. The integral of that is negative 50x squared, which basically means it's a parabola that opens downward. So how high do I go now? The question is answered by, again, the area under the slopes. I mean, under the curves. So, for example, here, that's where I started. Where do I end up? I add this area. This is where I left off. Where do I end up? I add this area. And I add them because they're positive areas. So this negative 25, I'm going to add a 63.28. And I end up at positive 23.28. But where exactly is that? Well, that is at x equals 3.125. So this is 3.125 is about an eighth of the way. So right here, this is my 38.28 Newton meter. And then at the very last one, look at this. This is a negative area. So when I subtract negative 38.28, I end up back at 0. So what does this look like? It looks like this. A parabola that goes up, and then a parabola that comes down, and it ends at 0. So let's take a look at our graphs. 12.5 constant, jump because of our external load, negative 100x, and then a little jump right there because of a reaction force. So this is what our shear diagram looks like. This is what our moment diagram looks like. We start off at 50 because of the 50 Newton meters. And then we jump up to negative 25 because to that negative 50, we're going to be adding a positive area of 25 Newton meters. And then we jump again from negative 25 to 38 because we're going to add a value of 63.28, which is the positive area of this triangle. And of course, our peak happens to happen every single time that we cross the x-axis. Right there. That's our peak. And then at the very end, where do we end up? Well, we subtract negative 38.28, and we end up back at 0. So this one happens to be right there. And if you think about it, whenever you have a curve, what is the slope of the curve? It's basically the derivative. So the derivative of this will give you this value. So what's the derivative here? At this point, at 3.125 is 0. What is the value of our shear? 0. So that makes perfect sense. So I went ahead and I did this in, it was a suggestion that I made a while back. It is called Beam Guru, in which you actually go online and you put in your, you put in your length of the beam, the external loads, distributed loads, and I went ahead and I did this problem, this exact same problem on Beam Guru, and I'm going to show you. Let's see, what is this? Oh my goodness. Yes. Let's see, example 6. Let's go ahead and open it. Open with, there you go. And let me move this a little bit that way. That way you can see it. Here we go. So let me minimize. I'll just move it around. All right, so this right here is the problem that we're looking at. Let me zoom a little bit too small. It's either too big or too small. My goodness gracious. Sorry, getting used to this computer. All right. So there is our shear diagram. As you can see, it kind of mimics ours. It goes from 0 to 1250, straight line, all the way to 112.5, and then it goes down to negative 87.5, which is exactly what we got, as you can see from here. 12.5, 112.5, negative 87.5. So this is what we're looking at. And then for our moment diagram, we started out at negative 50. I think my screen froze, but luckily it froze on the diagram that I needed. Negative 50 to negative 25. As you can see, that's negative 50 to negative 25. And then it jumps up to 38.28, which is what I got, 38.28, and then back to 0 again. All right. So this, all it takes is some practice, guys, to understand that the areas under the curves, above 0 have to be positive, below 0 negative, and those pretty much tell you where you're going to be ending up. You're going to be adding those values to whatever value you're currently in. Hopefully this helps. I wish I could make another one, but I have a class to attend to in just a few minutes. And if I have time, I'll create another one, but I know your exam is tomorrow. So best of luck with that. And I hope this helps you a little bit at least. Thank you.